Hello, in this video we will be discussing time specifications, which are parameters or variables or measurements that allow us to talk about the shape of a response, of something that can be modeled as a second order system. Um, in these examples, we'll be looking at the step response of some systems. Um, and a step response is um, the response of a system to what's called a step input. To a step input. Oops. And a step input is a particular function where f of t equals, and it's going to be piecewise, so we'll have a little bracket. So f of t equals 0 for t less than 0, and it equals some constant c for t greater than or equal to 0. For a specific case called a unit step input, which we call u of t, that constant equals 1. So if we're going to draw this input on a plot, it would be something, it would look like this, where for all time less than 0, the input is 0, and then at time t equals 0, we immediately go up to some constant non-zero input. So this kind of input, when you think of it as a forcing function, it's analogous to turning on a light, turning on a motor, starting to power a system, things like that. And so a step response is often going to look something like this, where you start at 0, and then the system will respond and go up, and then begin to oscillate around some equilibrium point. I'll go ahead and redraw that because that wasn't a very good drawing. That's better. So the system starts to go up and then starts to oscillate around some equilibrium point that we'll note as y steady state. So now let's move on to some time specifications. So most of these talk about the amount of time it takes for the system to do something. And the first one that we'll discuss is rise time. So rise time is the time necessary for a system to go from rest, system to start from rest, at a certain ratio of its steady state value, to a second ratio of its steady state value. So, for example, the time it takes for a system to go from 10% of its steady state value to 90%. And if we come back up here, so our steady state value is marked right there. And if we were to say the rise time from 1 to 90%, we would find where the system has gotten to 10% of its steady state value, approximately right there. And we would find where it has gotten to 90% of its steady state value, approximately right there. We would measure time in between those 2 points, and that would be the rise time, T rise. And whenever you're talking about rise time, you need to specify which ratios you're talking about. There are a couple equations. So if you're dealing with a an underdamped system from 0 to 100%, and this only works for underdamped systems because technically a critically damped or an overdamped system will never get to 100% of its steady state value. So that's one of the reasons we talk about rise time and ratios. But if you're dealing with a underdamped system, then the time to get from 0 to 100% of the steady state system of the steady state value is 1 over omega d times pi minus a tan of 1 minus zeta squared over zeta. And written another way, omega d, we'll remember, is related to the natural frequency. If you're able to measure the rise time, then you can get the natural frequency is 1 over t rise times the square root of 1 minus zeta squared times that same quantity, pi minus arctangent of square root 1 minus zeta squared over zeta, like so. So you can do these two equations again. We'll say that these apply for underdamped systems when rise time is considered going from 0% to 100% of the steady state value. We'll go ahead and take a break there and do the next time specifications in the next video.